You are looking at a maintenance technician's worst nightmare. A piece of heavy industrial equipment that was supposed to be dead suddenly springs to life while someone is working inside the danger zone. OSHA Standard 1910.147, the control of hazardous energy, was designed to prevent exactly this. Yet Lockout Tagout remains one of the most frequently cited violations, resulting in severe injuries and fatalities, even in modern facilities fully equipped with the latest safety hardware. Facilities rely on these tools. The red multi-hole hasp, the heavy padlock, and the high-visibility danger tag are standard physical restraints meant to isolate energy. But clipping a lock onto a switch does not automatically guarantee a zero-energy state. To understand why the hardware isn't enough, we must look at the strict definitions governing this process. There is the authorized employee, the technician applying the lock; the affected employee, the person who operates the equipment; the energy isolating device, the specific mechanism blocking the power; and verification, the absolute confirmation that the isolation actually worked. When an investigator arrives after an incident, they rarely find that the cause was simply a missing padlock or a lazy worker. The hardware is almost always present. The failure occurs in the gap between the written rules and the physical execution. If the physical tools aren't the primary point of failure, we must look at the human and systemic factors. Lockout Tagout inevitably breaks down at 3 specific conceptual points in the field. Let's count them down. Failure point number 3 is the template failure. Many facilities try to meet OSHA requirements by distributing a single generic policy stating that all machines must be locked out, leaving the actual equipment-specific details as blank fields. This forces the authorized employee to conduct a real-time hazard assessment from scratch, usually under the intense pressure of a maintenance deadline. Relying on a worker's memory during an outage is an administrative failure. The danger of these generic instructions is that they bias technicians towards the most obvious energy source, electricity. A worker flips the main breaker, assumes the machine is safe, and completely misses the hidden power trapped in the system. Look closely at the mechanics of this press. An elevated metal platen possesses gravitational potential energy directly proportional to its mass and height. The hydraulic cylinders holding it up contain pressure equal to their volume multiplied by the system's force. Shutting off the electricity does absolutely nothing to bleed that trapped pressure or mitigate a fatal descent. To prevent this, a machine-specific procedure must explicitly list every single isolation point. It must detail the specific mechanisms to release stored energy, and it must outline the exact sequence for a safe restart. The immediate fix is to establish a master equipment inventory. From there, your team must physically walk down and verify every required isolation point on every machine. You also need a rigid change management trigger. The moment a piece of equipment is modified, an alert must automatically flag that procedure as requiring a mandatory update. A generic template creates a hidden liability the moment a technician encounters equipment that the document wasn't specifically designed for. Failure point number 2 is the verification gap. You can apply the locks perfectly, but that physical action is useless if you skip the most critical phase of the process, verification, commonly known as the try or test step. This diagram outlines the full Lockout Tagout tryout sequence. Verification is not a single button press, it is a multi-stage workflow. You verify the primary isolation is secure, you verify all stored energy is bled or blocked, and finally, you attempt to operate the normal controls to ensure the machine cannot start. In complex field environments, technicians frequently encounter mislabeled remote disconnects. Without the try step, a worker might lock out what they believe is the correct switch, completely unaware that a parallel sneak circuit is keeping the end machine fully energized. Another major trap involves latent energy residing inside the components themselves. Variable frequency drives can hold lethal charges in their capacitors long after the main power is cut.
Pneumatic lines can trap compressed air behind check valves, just waiting to actuate a cylinder. The solution is strict adherence to the sequential flow. Apply the lock, bleed the lines, block the mechanical components, and physically try the start button before ever crossing the machine's safety perimeter. In cases involving complex electrical systems, pushing a start button is insufficient. you must require a qualified person to use a rated voltmeter to test the specific circuits and confirm zero voltage. Lockout without verification is lockout and hope. Failure point number 1 is the authorship disconnect. When environmental health and safety managers write procedures from a desk, they create policies based on how they imagine the work happens, rather than how it actually happens on the floor. Maintenance mechanics must be at the center of this process. They are the ones who understand the technical reality of the equipment. They know about the bypassed interlocks, the temporary jumper wires, and the real-world operational quirks that an office-written manual will never capture. Production and sanitation teams also need a seat at the table. They manage the daily operational hazards, such as aggressive wet washings and complex machine teardowns, which introduce entirely different energy control variables. A single author cannot anticipate every systemic variable. Look at the diverse array of hazards present in a single facility, from thermal steam and chemical pressure to high voltage and biohazards. It requires a cross-functional team to accurately map these out. To bridge this gap, move your procedure writing workshops out of the conference room and onto the shop floor. Make it mandatory that an experienced maintenance mechanic explicitly cosigns every new or updated lockout procedure for technical accuracy. A procedure is only as good as the mechanic who agrees with it. The annual retraining requirement under 1910.147C6 provides a mandatory mechanism to audit your current procedures. During these sessions, you will often hear technicians push back and say, "We don't actually do it that way." Treat that feedback as critical diagnostic data. It points directly to where your written procedures have decoupled from reality. To leverage this, run a live physical lockout on a piece of equipment during the retraining session. Use the written document step by step to stress test its accuracy against the actual machine. If you find deviations between the paper and the physical action, establish a strict service level agreement. Those procedures must be corrected and updated within 30 days. This physical validation naturally facilitates cross-training. Safety managers learn the exact mechanical realities of the equipment directly from the people who turn the wrenches. Simultaneously, mechanics grasp the legal and engineering intent behind the compliance rules. Operators learn the precise physics of why attempting a start proves an electrical contactor hasn't welded shut. Active physical validation is the only mechanism that aligns the illusion of paper compliance with the concrete reality of shop floor execution. Selective adherence to LOTO protocols reveals a system that has decoupled from the reality of daily maintenance. When workers choose when to follow the rules, they are signaling that the written procedures no longer match the technical requirements of the machine. That breakdown originates from 4 root causes: persistent training gaps, a lack of operational context, weak supervisory enforcement, and written procedures that contradict operational reality. First, you must fix the foundational templates so they account for all physical energy profiles, not just the electrical main. Second, you must make the verification sequence an unskippable, concrete part of every maintenance workflow. Third, you must put the maintenance and operations teams directly at the procedure writing table. And fourth, you must use your annual retraining as a physical audit to continuously update your documentation. Executing these 4 steps together removes the guesswork from hazardous energy control. It is the only way to guarantee a true zero energy state every time, without exception. If you want to learn more about workplace safety and OSHA rules, subscribe to HSEstudy.